Tell Dr. Dong what you've done, Benji. Dr. Dong, he has something to tell you.
She's very intent on me telling you that I didn't have the chocolate yesterday.
Because he didn't realize it was chocolate.
The chocolate thing that he gave us yesterday from the lab, I didn't eat it because I knew it was chocolate.
I'm so disappointed in you. That's such a waste. It was so good.
Bad. This is probably start strangling me.
Then he realized it was chocolate. He threw it away.
I had some of it, but I didn't think it would taste that good. I thought, no, this is the good chocolate. I'm not supposed to eat it. I'm going to throw it.
That's even worse. The fact that you ate it was like, wait, this isn't something I'm supposed to eat, and didn't tell anybody. That's dangerous.
I figured no one else would be as stupid as me.
Oh my gosh.
A lot of people are dumb as you. The question is, are you as dumb as I'd like to think not, but I probably am.
What are you doing? Go away. Well, don't. I can do it myself.
No, you can't.
Maybe I don't want it to become.
You're an app. I think you may have just got How is there an iPhone detected?
I don't know.
What did you do, Micah? You started messing with her.
Stop. You stop. You stop. This is my laptop. I have the right to do what I want. See, I fixed it. Unfortunately. Wait, that's not what you said. I don't want to be alive.
You were the reason why suicidal thoughts happen.
Oh my god, Micah, no. He's the person who saves us from it. Blame the class, not the teacher.
Okay, blame the student, not the teacher. Micah! Can you,
and then just sit down and write everything that next day. But, that's ridiculous.
You could give us all A's.
That was back before kids, so. Alright, so as promised.
What?
A's for everyone.
Ooh, I like that idea.
As promised, we're going to class a little bit, right? We're now mostly done with the class. The bulk of the material for the class, the bulk of the stuff you've done needs to do for this class is over. Okay, for good or for ill, it is now done. And so we do have a final, but I feel like let's not talk about things like that yet, huh? Yeah. Let's talk about something fun. I have a bunch of different things to talk about, and I'd love to talk about something. Let me start, and you guys can listen. Yeah. Yeah. You have a what?
Are you going to have
yeah, I will have to decide on that. I think we'll have time because I should have these graded by Monday, and I think that's enough time. So yeah, we'll see. I'll have to decide. And plus, maybe I'll look at it and be like, that's not necessary. I'll do something else like that. So I feel it's better to wait till after I grade it, and I think I have enough time for that. Okay, so we have plenty of things I can talk about, but let me start with particle physics and what Feynman diagrams actually are. We never really talked about that. So let's talk about it. So let's start with the double slit again. Okay, now remember that double slit interference, of course, happens for all particles, not just light, right? Like we said. So you send something through, and what happens, it kind of goes through both of them, right? So if I refer to this one as psi1 and this one as psi2, the wave function of the particle reaching the screen would be psi1 plus psi2, right? Because it kind of goes both ways, that's where everything comes from, right? There's the whole interference thing happening. Okay, now, suppose this argument is due to finite. Suppose I now drill a hole right here. What's going to happen? Well, it's going to be more thing, and if I call this thing psi 3, then you would add in psi 3. And this has its own invariant letter, which is like blah, blah, blah. Okay. And then, suppose I build 2 more holes. So there's one up here, and there's one down here. So you see we call this psi 4 and psi 5, right? Well, then you would have plus psi 4 plus psi 5. Okay? Now, suppose I keep on drilling holes everywhere in this wall, just all over the place, okay? I keep on drilling holes all over this wall.
That's like a $17 charge.
Eventually, you'd be quite right? Eventually, I keep drilling holes until there is no wall left. Right? And then I could, if I wanted, I could also do something like I could put in another wall, right, with holes in it, and like drill holes in it, and then you get paths like this, right? They go through here, then go through here, right? You see what I mean? You get sort of zigzag paths, right? And I can keep drilling holes in that too, and I would keep on going, and I can build in more walls so that eventually you'd be able to end up with paths like this as well, right? Because if I just put walls and made holes in them, you'd end up with paths like that, right? And so if I keep building all these walls and then keep drilling holes in them, what do I have left?
A lot of
If I drill holes in them, what do I have left?
No. 04.
Okay, what I have left
No?
is that
That's
this
not
has to
how
be
it's
equal
calculated?
to this. Right? Because I kept drilling holes in them until there's nothing left, like Rayla said. So, and where does the light go from here? It just goes like that.
Gas.
Right? Right.
No.
So, what we're saying is that this and this are the same thing. And so, this is an argument due to Feynman. He, of course, did it in a more complicated way mathematically, but it's referred to as the Feynman path integral. And the way he says it is the path of a particle is the sum of all possible paths. Okay? The path of a particle is the sum of all possible paths, he says. Well, you can reformulate all quantum mechanics in terms of the path integral. It's hard, and it's not like it's that straightforward, but it turns out to be really useful for taking quantum mechanics, if you want to take quantum mechanics and add special relativity to it. Which, do you really want to do that? Well, yes, because electrons, they go fast, you know? And so then, now you're going near the speed of light, now you can't just use simple quantum mechanics anymore, because you need a speed of light limiter in it, right? The quantum mechanics I taught you has no speed of light limit. The real thing must have a speed of light limit, right? So, from using Feynman path integrals formulation, it turns out to be the best way to construct what we call quantum field theory, which is relativistic quantum mechanics. Okay?
You have to learn a lot of quantum field theory.
Do I? Yes. Do you know? The thing they say, which is, okay, I don't know who exactly came up with this, but a professor who said, well, if you learn special relativity in a day, which you don't, but anyway, supposing you could, right? So he said, if you learn special relativity in a day, then quantum mechanics would take you a week, and then general relativity would take you a month, and quantum field theory would take you a year. But since you don't learn special relativity in a day, that means quantum field theory takes a lot longer than that, right? But that's roughly the scale of difficulty that we're dealing with. Quantum field theory is horrendously complex, and it's just special relativity. It's special relativity mixed with quantum mechanics, and it's basically you take e squared minus b squared equals m squared, replace e and p with operators instead of variables, right? And then try and go from there. And it's very hard and complicated, but here's what it deals with. The way quantum field theory works is it looks at a particular interaction. Let's take a simple interaction like this. Okay? And this is quantum mechanics now, right? So you cannot say, does this happen? You can only say, what's the probability that this happens? So the question is, what is the probability that this occurs? Okay? So when you take an electron and a positron and throw them together, different things can happen. One of those things is they become ionized. The question is, and the only question you can answer is, what's the probability of getting that interaction? Right? That's really the only thing you can answer in quantum mechanics, right? So this is the question. Now, to figure out the answer to this, to figure out this probability, we discover that units of probability are often not helpful. So what we do is we borrow an idea from classical mechanics, which is if you, let's say that Timothy's over there and John's over here, and let's say they are shooting guns at each other. Okay? Now, if you're shooting guns at each other, what kind of gun would you want to use? No, of course not.
Phaser.
Laser is not a gun. What kind of gun would maximize your chance of taking?
Dangerous one.
RPG. What? RPG.
RPG gun?
Yeah.
That's not a gun.
A Gatling gun.
What?
Yeah, Gatling gun is a type of machine gun, right? Okay,
RPG.
so they're firing machine guns at
RPG
each other,
stands
right?
for
Now, here's the issue.
Oh.
With a machine gun, what's the advantage of a machine gun? It fires very, very fast.
What?
Really kind of absurdly fast, right? It's like half a second. Well, it depends on what you're trying to do. So, machine guns fire very fast. But there's another issue with the machine gun. If you fire very fast, what is something else that you might have a problem with? Well, that's too.
Well, I mean,
But it's not just about the speed with which you fire. Another thing that counts is the accuracy and the precision with which you fire, right? You want it to actually go in the direction that you point. Okay, so here's the thing. If John is firing this way and he wants to hit the wall, he's got a good shot at it, right? Okay, if he's firing this way and he wants to hit
the speaker.
The little like poster, the folder that's pinned to the wall there, there's a one that we light on. If he wants to hit that folder, right, then it would be more difficult, right? If he's firing this wall this way and he wants to hit a particular letter on that folder, then more difficult, right? And so, if you think about it, there are two things that are going on here, right? One is the precision of John's gun, right? That affects how often he'll hit his target, right? The other thing that affects how often he'll hit his target is, well, how far away is also you're right, but also how small the target is, right? So the target matters as well, right? Make sense? Okay, so if you want to say what's the probability of John being able to hit a target, right? The probability of John being able to hit a target is going to rely on a lot of different things. It's going to rely on the target, and it's going to rely on John too, right? Okay, so what we do in physics is we separate the two things. You separate the firing part from the target part into two different calculations. So what you really need to know is so this is all classical. This is an analogy that we use in physics, basically. So if you're trying to do that, what's the relevant thing about the target that you would want to know? Size. What does size mean? Be specific. How much? What? Surface area, right? The what area matters, right? The lateral surface area. What do you call that? You guys don't know this word? So in other words, if it's a big, like for example, if it's a big long canister, it doesn't matter if you're shooting at this end, right? The only part that matters is the area of the cross section, they call it, right? The cross sectional area, right? In other words, only the part that you see matters. Just like, right? If you're firing at something that's like long this way, it doesn't matter about being long this way. It's only this part that you see that matters, right? Okay, so what matters is the cross-sectional area. Okay, so what we do is we look at the cross-section. This is gonna, sorry, I should give you a warning. This part will be relevant to the final.
So much for
Sorry, I
being
actually
fun.
wasn't going to talk about this right now, but it fits so naturally right here that I think we're talking about it. So I was going to say it really, but like it fits really well right here. So we talked about that, right?
What's the dong?
want
Having
to
a
not
good
be
day.
This part, like, if I'm having a cross-control part, you don't need to worry about. But what a cross-section is definitely. Sorry, like I said, I was going to go another direction, but it fits really naturally right here. So let's just talk about it right here. Okay, so we want to know the cross-section. Okay? The cross-section would therefore, I'm talking, in classical physics, the cross-section will have units of? Yeah, some area, right? It's an area. It's a cross-sectional area is what you're firing at, okay? We are using this analogy to use it the same way. So this is going to be an area, right? Okay? So the cross-section of an interaction is going to be, it's roughly how hard is it to hit the target, right? Okay, now the other side of things needs to be John's gun, right? So what? Now we've talked about the target itself, right? Now let's talk about the thing that's firing the gun, firing the target. Okay, what's relevant about that matters? Okay, the accuracy really means what? Okay, well, what does it mean?
Probably.
Okay, good. Which means when you fire, there's a spread, right, to the bullets that come out, and so you want to know how big is that area over which they spread, right? Okay, what's another thing that's relevant? The size of the bullets is, let's assume, sufficiently small to not be relevant, because we're talking about particles here, right? So what else matters if you want to know how frequently will John hit the target? Then what else do you want to know?
How big is the target?
How big is the fire, right? Okay, so we want something that deals with, we want to know, roughly speaking, we want to know hits, we call it hits. So we have something that's going to be in terms of hits per
Minute.
per time, right? Let's just say, well, let's be specific. It's per second, okay? And it depends on that spread of area matters, right? So it's also going to be per square centimeter. Okay? So in other words, if you were a square centimeter over there, right, in 1 second, how many times would you get hit on average?
5.
Oh! That was just in Dr. Skinner's class. Skinner knows whenever you say something smart. That was smart. Yes, that's exactly right. This is a definition of luminosity.
Oh, hey.
Aha. I didn't really define it for you before because I didn't have time. Okay? But luminosity is how do I describe this? How often do you hit stuff? Okay? So the luminosity is how good are you at hitting things in general. The cross-section is how hard is the target to hit. Okay? Now, going from luminosity, so let me give you the names, the symbols for these. Cross-section is demonstrated by sigma, lowercase sigma, like that. That's the symbol for cross-section. Luminosity is always done by script L, okay, cursive L. Okay? So that's luminosity. Now, usually, I mean, a rate is often important, but John only has so many bullets, right? So the question you really want to know is, if John fires all his bullets,
What percentage of them will hit?
how many times will he hit the target, right? Okay, so what we first need to know is there's a certain amount of time for which this will lapse and then it ends, which is what happens in real experiments, right? So we can move from here to a concept that we call integrated luminosity. What's integrated luminosity? Integrated luminosity is total hits per square centimeter. In In other words, you have summed up all the hits over a certain amount of time. Okay? The symbol for this is the integral sign. Okay? Those of you who know calculus recognize that. If you don't worry about it. It's not a big deal. Okay? The important thing is integrated luminosity means how many times total, right? How many hits total are there per square centimeter, right? So this is how many times did you hit stuff? Just total, right? Not a rate anymore, but just a total amount. All right? Now, here is the important part. Cross-section times integrated luminosity equals number of events. Okay, number of hits, if you like. Okay, the cross-section is how hard it is to hit the target, right? How small is the target? This one says how many hits do you get in a given square centimeter. If this is in square centimeters, you multiply them together, you end up with a unitless quantity that represents how many times does the target get hit. Okay? Make sense?
Yes.
Okay. Now, here's the idea. We do the same thing, except our targets become a lot fuzzier. Okay? It's no longer just an object here and you are trying to hit the target. Instead, the target now becomes an interaction. Okay? When we say hit the target, we mean how often does the interaction occur? So as before, there are two different pieces to it, like cross-section and luminosity. The cross-section is the fundamental piece. So now we switch it into quantum mechanics mode, into physics mode. Then cross-section equals how hard is it to make the interaction. So it's sort of a fundamental quantity, like of itself, how hard is it to make the interaction? And then you have the luminosity, which is how often do you try? Okay? So, how hard is it to make the interaction is going to be something you calculate from theory. You can also measure it, of course, but it's something you can calculate from theory. Give me an example. What would be an interaction that has the kind of interaction that has particularly low cross-sections, small cross-sections? Like any more? Okay, interactions with hot force. Neutrinos interact with weak force, right? So those are low. That's also a low. We already talked about things that don't happen much, low probability or low amplitude for happening. That's the same as saying low cross-section, small cross-section, right? So this is calculated via what? Lyman diagrams. Exactly. This is done with Lyman diagrams. And this, the luminosity depends on what? So it depends on your particularly one part of your experiment. Yes, your accelerator, right? This part depends on your accelerator. Right? Right. This part depends on your actual interaction that you're looking at. This is determined by your accelerator experimental sum. Okay? And so those two together determine how many times does this actually happen. All right. As you may have noticed, luminosity is in per square centimeters per second. That's what the units of luminosity is. And one of you groups messed that one up. But anyway, the one that we focus on is integrated luminosity. So here's the thing. You may have noticed when we calculate luminosity, you got a ridiculous number with scientific notation, right? So when they first made this kind of jump to looking at things in terms of cross-section, here's the thing. We're looking at an interaction happening. It's not actually about things hitting things anymore, right? It's just about whether an interaction happens. But we use the same language, and therefore we still calculate it as an area, even though it is no longer the area of a physical object, right? You can still calculate it as an area. The units are still units of area. But square centimeters, I mean, square centimeters this big. Are any particles this big? You know, like what the particle that size is ridiculous, right? So we don't use that. The unit we use for cross-section, cross-section is measured in arms. You're like, really? Barnes. You're like, oh, I know. That's named after the great some physicist named Barnes, right?
Can't hit the broadside of a barn.
No, it is named after a barn.
Yes.
Why?
Don't. Because you can't hit the broadside of a barn.
Okay. The one barn is 1 times 10 to the negative 24 square centimeters. So a little more respectable for a particle, right? Well, only a little bit. It turns out that this unit was chosen. I don't actually know exactly who chose the unit. Some guy chose this unit, but it's the size of like a hydrogen atom. Okay? Well, if you are an electron, how big is a hydrogen atom? Very huge. Okay? So if you're talking this in cross-section, you're still imagining like John now shooting electrons, and that's the hydrogen atom over there. How big is that hydrogen atom?
A barn.
It's like to hit that hydrogen atom would be like hitting the broadside of a barn.
What did I say?
And
You
so
said that,
this
okay.
thing as a barn. So stupid. Okay, so the unit we use is barns. Now the problem is a barn is gigantic. That's why it gets the name. So we never work in barns. Therefore, we use SI units, right? The barn is an SI unit or close enough to an SI unit. I mean, it's metric, right? And so we use SI prefixes. And so, for example, the top cross section, the top quark production cross section is measured in picobarns. That's a lot of barns. No, picobarns. So it's 10 to the negative 15th, 10 to the negative 15th barns. Because that's actually the scale at which we work at. Okay? The interaction cross-section at the LHC, which means what's the cross-section of, what's the odds of it hitting anything at all? You know? The interaction cross-section of the LHC is millibarns. Okay? Which is pretty big. That's because they squeeze them down really tight and they have a lot of protons. And so they get an interaction cross-section in the millibarns. Okay? So you have picobarns, nanobarns, millibarns. Microbarns, and very much femtobarns, yeah. And they're all just the SI prefixes on the barn. Okay, well then, what do we measure integrated luminosity in? Well, the fact is, normally this is a really weird number with a lot of scientific notation, right? And it's all in like centimeters squared per second, and you're like, you don't think about things in terms of centimeters squared when you're doing particle physics, right? So, we know we want the integrated luminosity to cancel out units with the cross section, right? So if the cross section is going to be in picobarns, we're going to put our integrated luminosity in inverse picobarns. That's right. So this is now measured in inverse barns. That's to say, you write inverse picobarns or inverse femtobarns. Okay? And you're like, what? Well, because you want it to multiply with barns, then it'll cancel out. So, but keep in mind, which is bigger, an inverse, so femto is one of the smallest, right? 10 to the negative 18. Pico is 10 to the negative 15, the next one up. But which is bigger, an inverse picobarn or an inverse femtobarn? The inverse femtobarn is bigger because it's 1 over 10 to the negative 18th, right? So an inverse femtobarn is freaking huge, right? Whereas an inverse picobarn is small, right? So it goes like the opposite way, it was 1 over that. So the total amount of data running at LHC that they've collected at the LHC so far is about 30 inverse femtobarns, which is ridiculously large amount of data. Okay? So that's the integrated luminosity. The cross sections of the events they're looking for, though, are measured in picobarns and femtobarns. And so, how many events do they end up getting? Somewhere between, you often get, 1,000 candidate events, of which 100 are your real events, or something like that, right? So even with this giant crazy accelerator running nonstop for years, except that it's in Europe, so they have to take a break every summer. In America, the Tevatron ran nonstop. Like, it didn't stop unless it broke down. In Europe, they stop every year. They take a few months off every year because it's Europe. You gotta do that. That's one of the differences between America and Europe. Americans are more productive and Europeans are happier. So,
which is more important?
You tell me. Well, you're American, so.
Which am I supposed to say?
Okay, so this is the idea of cross-section. Very, very important. So cross-section is the interaction with the cross-section. The luminosity comes from your experiment. If you know both of those, you can calculate a number of events. Okay? The other thing that they can do with the cross-section is something that we do with the cross-section is something called a branching ratio. Okay? And a branching ratio is it's a ratio. Good, right? So here's how a branching ratio works. So this one's actually a very useful one. It's the fraction of the time something happens. So for example, you have the cross-section of, say, a z boson going to e plus e minus. Okay? That's a specific interaction. Divided by the cross-section of z boson going to anything.
Oh.
Okay? So what does the branching ratio tell me? I can't actually hear you facing the other way. Good. This is the probability now of a z boson going to e plus e minus, right? This is z boson doing anything. This is z boson going to e plus e minus, right? So it gives you a fraction, a probability. How often does this happen? This, therefore, is an easy one to interpret. And so people use branching ratios a lot because it tells you this percent of the time this will happen, right? For example, one I happen to know offhand is top quark decaying to WB divided by top going to, they usually just write x, meaning anything, okay, is like 0.99, turns out. So tell me what that statement means. Yeah?
That means most of the time when the top quark decays, it decays into a bottom end of W.
Very good. How often?
0.99.
99% of the time, right? I think it's actually more than 99%. It's very, very common. Okay? So this can be calculated by theory. So this is things you can do with cross-sections. You can calculate how many events do you expect for a given amount of luminosity, or you can calculate what's the fraction of something happening by dividing the ratio of the cross-sections. Okay? So you think of it, cross-section sort of is proportional to the probability of it happening. Do you have a question?
How do you calculate something like that by theory? You can postpone that question.
No, that's actually where I was going.
Oh.
So, but I realized I wanted to first motivate why we want to know it, right? In a sense, this is all we can measure about particles, or about particle interactions, is cross-sections. It's really all, because that tells us all the probabilities we want to know can be calculated from the cross-section. And so in a sense, the cross-section of an interaction is the only thing we can measure and predict. Plus the other, the quality, the mass and stuff like that, right? Okay. So let us talk exactly about what Dave said. Let's say, how do we calculate this sort of thing? Well,
Careful.
here's how we do it. We have a particular interaction we want to calculate the cross-section. So E minus E plus goes to mu minus mu plus. All right. Now, okay, so this is the only things that are observable, right? Is that you started with E plus E minus, you ended with E plus E minus. That's all you know for sure, right? So as a result, you do not say, oh, if I'm in diagram, annihilation photon, blah, blah, blah. You do not say that, okay? Instead, you say this.
Wow.
Say U minus E plus goes, something happens, and U minus U plus comes out. All this is not observable, right? Therefore, you just say something happens. IMSA kids refer to this thing as the waffle. No one else refers to it that way. Please don't say that outside of IMSA. No one will know what you're talking about. I know this because Jen Byers, I still remember my first year, her following year goes to Reed College, and writes me an email that she was impressing all her friends because she was majoring in like English or something, but she's like talking about particle physics and stuff like that. Her friends are like, oh, how do you know all this stuff, right? And then she's like, I impressed them with everything. I told them about all the stuff about the things, but when I said the waffle, they had no idea what I was talking about. And I'm like, yes, no one called it a waffle. You know who calls it a waffle? Charlie Fry. It was Charlie Fry's fault. He started calling it a waffle, and then everyone started calling it the waffle. And then like, yeah, what else is this called? Nothing. You don't need to name it. I mean, waffle's as good a name as anything. I mean, it's as good a name as barn, right? Like, it's really worse. So,
If enough of us start calling it a waffle,
it's better than Charm and Strange. I'm with anything is better than the names of supersymmetric particles, right? Yeah. Wait, did I tell you guys the names of supersymmetric particles? I think I only told the other class. Oh, you guys gotta know this. Okay. You don't need to know this. You just gotta hear this. Like, it's ridiculous. So the supersymmetry is a theory not verified that predicts that every fermion is a boson counterpart, and every boson is a fermion counterpart. Their counterparts would not be any of the existing particles we know. It has to be a new particle. Okay? So these new particles all need names. You need to name a whole bunch of particles in a hurry, right? And so what they do is they came up with a standard naming convention, the stupidest one you could possibly imagine. It goes like this. The boson partner of a fermion you could name by putting an S at the beginning of the words. So they refer to collectively as spermions. Okay? The spermions are made up of squarks and leptons. Okay? And they have all the same names. The leptons are the selectron, the smuon, and the stau, right? With their corresponding neutrinos. And then the squarks are sup and stout, strange, and stop and spot, right? Okay. Yes, no, so there are searches for stop squarks, and people say these things with straight faces. I imagine we have a lot of people from around the world who are doing English as a first language at the Fortune Fermi Lab, or actually, I mean, English is the international language for physics, right, for science in general. So a lot of people are learning English from other things. They probably think English is a really stupid language. Like, wow, how do people squirrel? I mean, they're right. It is a stupid language. You're correct. But, and then for the bosons, they add eno to the end to get the fermion counterparts. They're called bosinos. The bosinos are the photino, the gluino, right? The gravitino can exist. Then there's also, of course, the wino and the zeno, right? Zeno. Yes, exactly. So dumb.
Sounds like we genetically uplifted snakes and then.
So yeah, I mean, it's just like snakes. I don't actually know. Fortunately or unfortunately, I don't know the strange quark is like right in the middle. It's not something people are searching for, so you don't have to hear about the strange. But I don't actually know how else you would say that.
So you spell
it?
it?
Distinguish it from the strange.
So you would spell it S-S-T-R-A-G-E, but they're different.
I mean, so dumb. So dumb. So anyway, when you compare that, like also doesn't sound too bad. There's another theory that came up with a sort of analogous thing to color that was like basically another kind of force-like thing, charge-like thing like color that they introduced to that theory. It's not been proven. Actually, probably not true, but the main versions of it have been disproven. And so it's sort of like color, but it's different. So you know what they call it? Technicolor. Right? Oh my God. So anyway, yeah, they do a bunch of this stuff. It's just like so dumb. The only good particle name we've come up with is the axion. That's a cool name. Axion is a cool name. I don't know. Like, I don't understand. An axion is like a weird excitation. It's like an excitation in the anomaly of the QCD field. I do not understand it. It's a dark kind of name. But I don't understand where it comes from. Okay, back to this. Okay, the point is, we don't know what happens. We cannot observe what happens, right? So this is what actually happens, right? Because this is what's observable. So what we need to do, of course, is figure out the probabilities. But the probabilities are not as straightforward as all this, because these guys have specific energy and momentum, right? So really, the probability there's a probability of going from E1 with an energy of a certain energy and a certain momentum, okay? And then this one at another energy and another momentum, right? Going to the mu minus with another energy and another momentum, and then mu plus with another energy and another momentum, right? That's really what you have to calculate. And by the way, actually spin should be in there too. You end up putting these all together with their spin and helicity space into a 6-dimensional vector that you call a chiral vector, and don't worry about that. Anyway, so this is actually what we have to have calculated, right? Kind of a lot to calculate. So, and if you think about it, right, what do we really have to calculate? Well, you have to calculate the probability of all possible initial states going to all possible final states, right? So So in other words, you take these things and you have to calculate this one, and then you can change this to different. So then it's like, just imagine, this is 1, 1 going to 1, 1. Okay, then 1, 1 going to 1, 2, 1, 1 going to 2, 2, right? Okay, and then 1, 2 going to 2, right? And so a simple way to imagine this is as a big matrix. Okay, where on this side you have initial states, right? And that would be, E1, E1, E2, E2, and then there's the next entry, and all the different possible energies momenta you can have. And then up here you have final states, which are, that's the E3, E3, E4, E4, and all the different possibilities. Now, obviously, this would be an infinitely large matrix, but you can imagine it as a matrix, right? And so if you wanted to know a particular thing, what you would want to know is you say, okay, well, I have this energy and momentum. I want to know this energy and momentum. This is my answer here, right? Okay, and so this part here is very important, and it's called the matrix element. Always represented by a script N versus N. We run out of letters, so we start doing them in weird typefaces.
So, that explains so much.
Right? If the Chinese had discovered all this, it would be both easier and harder. They would never run out, they could just use the actual character, It seems like it'd be a lot easier in a lot of ways. But anyway, so you have the matrix element N. And then you see that the matrix element is related to going from here to here, right? And the rule is the cross section of the interaction is proportional to n squared. There's actually a few extra terms on there, but we'll say it's proportional. You guys know that squiggle means it's proportional to. Okay, so basically the important part of it is n squared. There's a few other terms on there, but those are unimportant. This is the important part. So if you know the matrix element, you get the cross section just by squaring it. Yeah.
So the matrix element is it the only element where like the initial state and final state matches, or like
right. So it's like the probability of going or the amplitude really. It's similar to a wave function, right? It's like the amplitude of going from here to here is this, then you square it to get your cross section, right? Now, in reality, of course, you don't write a gigantic matrix because that'd be ridiculous, it'd be too big anyway, right? What you do is you write this thing as a function of the energies, right? So the matrix element is written as a function of the energy and momentum, and then you can plug in any numbers and find the answer you want, right? So there isn't actually a matrix. We don't write a matrix, but we call it a matrix element, okay? Kind of, All right. Now, yeah.
the matrix element is a probability.
The matrix element is closely related. So the matrix element is close to a probability. It's like a wave function is close to a probability. Okay? It's not quite the probability, it's close. You use it to calculate the probability. How do you do it? You square it plus a few other things, and that gives you cross section. And from the cross section, you're able to calculate a probability in a particular situation. Right? So the matrix element is analogous to a wave function. Okay? It's complex in general, for example, right? Okay, so now finally, how do you calculate a matrix element? This is the fun part. Here's where you use Feynman's path integral. Okay? Feynman's path integral formulation says that you have to try every possible path, right? So how do you do that? Well, you have to take. Okay, we are now leaving the part you need to know. Okay. So do not freak out when I write the following.
Oh boy.
Okay, it's not that bad yet. Oh, it just got worse.
God.
What? I don't need this in my life. Wait, why is it TXYZ? Why is it TXYZ? Why is it XYZ?
Oh, of course. Gotta add that I. Oh.
Change the wave function.
Okay, now it's
It's to this power.
Okay, so like I said, you do not need to worry about this.
I'm writing it down anyway.
Responsible for what is, in some sense, literally the most difficult equation in the world. Like that actually might be true. So what is this? This is a path. Phi is so this is an integral, as some of you have seen, but which is like a sum over all possible numbers, but it's not a sum over all possible numbers. This is called a functional integral. It's a sum over all possible paths between 2 points. So I'm trying to get from here to here. This is all possible ways that can happen. That's the phi. What do you do to each one? You take the integral over all space and time, so a quadruple integral over that path, and exponentiate that. And then you sum over all possible paths. So, how do you do that? You don't. This is only solvable in the case of a single massless, spinless, colorless particle in an empty universe. It's been solved in that case, and it's still not that case. So if you add anything else to it, it just becomes unsolvable. Okay.
Like, effectively unsolvable or really unsolvable?
Okay, it becomes effectively unsolvable. It becomes beyond even the imagination of a computer. Not that they have imaginations. Beyond the imagination of a computer. Right? Like it is not even something you could imagine putting into a computer. It just becomes absurdly difficult. So you're like, great. So what do? We do this is always do with impossible problems. You get all the time. What do?
Cry.
Approximation. No, that's what the students do. This is no cry. We approximate. Okay. So what we do is we can actually take this, and no matter what this thing is, it's still just a function at the end. And so the relevant part of it is the lambda, which is called the coupling constant, which is basically the strength of the interaction. And so what we do is we can do a trick that's an approximation trick. This is used constantly called the Taylor series. Those of you who take BC3 know the Taylor series. A Taylor series is a way that says you can approximate any function by a polynomial, infinite polynomial. Okay? So what you get is something that looks like this. So you get some number, some constant times lambda, times some constant times lambda squared, some constant times lambda cubed, going on forever. Taylor's theorem says that for any real function, any function that actually exists in the world, you'll be able to do this. And it gives you a way to calculate these coefficients. So we're like, great. Okay? Okay, so that's cool. See, now we have the answer. No, we don't have the answer. Does it really help to write it as an infinite polynomial?
No.
It's an infinite polynomial, so not helpful, right? Because graphing an infinite polynomial takes a long time. Yeah, turns out. But we are saved by a special fact, which is that many times lambda is much less than 1. That's our much less than sign. I know, right? No, seriously, this is used all the time, the much less than sign. Okay, for example, for electromagnetic interactions using photons, lambda turns out to be approximately 1 over 137. That's pretty small. Why is that relevant? Because now each successive term is smaller than the one before it. And so, while I still can't calculate the answer, I can get pretty close because I know these other terms are getting really small.
There's a way to...
Right, because lambda to the third is going to be 2 orders of magnitude smaller than lambda to the second. So these coefficients, as long as these coefficients aren't going crazy, and they don't, as long as the coefficients aren't going crazy, then like, wow, we're onto something here, you know? So this is what we do. We approximate. And these guys are given by Taylor's theorem, which is a standard high school, now high school, used to be college, but they include earlier. It's something you learn in DC3. Standard formula, not even hard to do, right? And so you're like, great, easy. Now, the only problem is, applying Taylor's theorem to this is a little tricky. Also, I have simplified because really we need a Lagrangian term in here, and the Lagrangian is very complicated. So doing Taylor's theorem on this is doable. It is hard. So calculating these guys is really hard. At this point, you have 2 possibilities. You can, A, just don't screw up, idiot. This was the approach of Julian Schwinger, who shared the Nobel Prize with the other approach, which was Richard Feynman, who said, let's come up with a set of rules that we can remember so that we can calculate this thing without screwing up. And those rules he came up with by visualizing the mathematical terms as little lines that go into each other. And so these things are calculated by using a computational technique of Feynman diagrams. And so this thing, for example, for our particular interaction, the C0 term is the non-interacting term. It goes like that. Boring. Okay? So that's the Feynman diagram. Because of that, we basically always take the Z0 term out. Okay? Technically the C1 term is 0. The C2 term is this. Right? And you remember what was the word I used for that diagram? I always said you had to find the highest amplitude leading order diagram. Right? Leading order means highest up in the approximation. Right? So this is because this one we always ignore. This is 0, it turns out. So this is the leading order here. Okay? So we call that leading order. And then this one's also 0, and so let me add on the fourth term. Got it? This one is, so lambda is basically, the coefficient of lambda is basically the number of vertices you have. Okay? So this is 2 vertices, that's why it's lambda squared. This is all the 4 vertex ones, which look like, for example, this. That is 4 vertices, and this is 4 vertices, and this is 4 vertices, and a few others, right? Okay, these are not leading order, higher order diagrams. This one is particularly called next to leading order. And the next one is actually called next to leading order, and then next to next to leading order. That's actually what they call it. So a question, I thought so. Yeah, there.
What programs do you calculate the leading order Feynman diagram?
Yes. Program called, there's several now, but MagGraph is the one that I use that will do leading order Feynman diagram calculations. These are much harder and generally require specific ones. I think by now there's probably some leading order calculators out there. But in general, you have these calculations get really difficult. So computers can help, but can't do it by themselves. Yes?
So that whole Taylor series is equal to the matrix element?
Right. This whole Taylor series is equal, not to the matrix, yeah, it's the matrix element. Thank you, I got that part of it. Matrix element equals this. There might be a negative sign there, I forget. So, an interesting point to point out is that this is the whole term, so you have to sum these together. And since you're summing matrix elements that can be imaginary or complex, it doesn't always get larger, it can get smaller as well. The phenomenon we call interference, because it's interference, right? Meaning that when we introduce a new theory, this might have like a new possibility, it could mean the overall yield goes up, like the overall thing that you see goes up because it's like now a new thing that could happen, right? But it can also make it go down because that new thing that shows up could interfere with existing stuff destructively and make the total amount go down. The total cross section go down. So it's a fact that because that's because you haven't squared yet, right? You haven't squared till the very end, just like in Feynman. I mean, it is Feynman. Okay, so now we know what Feynman diagrams are. Each of these things represents a number, and that's it. The reason I always tell you to draw the leading order one is because the leading order one is by far the largest contribution to the answer. So usually, we calculate the leading order answer, and we're good. And then if you really care, then you go down to next to leading order, and you get a more precise answer. And then there are special techniques called resummation and stuff like that, where you can try and hit the later terms and stuff like that. But theorists spend a huge amount of time working on these things. I mean, like I said, computers help, but don't do it for you. There's just a massive amount of work that goes into calculating these diagrams. They're very hard. Okay. So now we know what a Feynman diagram is. Okay. It is a pictorial representation of a complicated function. When I say complicated function, it's all done in 6-dimensional vectors. And then you have these 6x6 matrices, and then you have this weird thing, the gamma matrix, which is a matrix of matrices. So it's like a matrix where each entry is a matrix. So a 4x4 matrix of 4x4 matrices. And then, so it gets really very complicated. And then, at the end, you finish all this work, and you're like, okay, I'm done, right? And they're like, you haven't talked about spin yet. And you're like, no! And so doing this exact interaction, took 3 hours of lecture time in my particle physics class just to derive this answer, right? The harder ones, like if you want to do QCD is so bad. You know why QCD is bad? What does QCD have what does the strong force have that the photons don't? Color. So now every Feynman diagram has like 8 different possibilities because of 8 different types of gluons. And so everything is multiplied by 8. And it gets like horrendously bad. And so those can take a semester to go through. Those you do one of those for your PhD thesis if you're a theorist. I'm not a theorist, guess why? Alright, so anyway, the part about cross-sectional luminosity is going to be key and you will want to know the final. Okay? This stuff is just fun. I just want to let you know that. I'm not testing you on that. Okay? Like I said, I didn't actually intend for you to have note-taking stuff today, but it did it nicely. So, we'll keep this up. Once I have final stuff ready, I will let you know. I will give it to you. In the meantime, I have some grading to do.
No, you don't. Just give us all A's and we'll be happy.
No, thank.
No, thanks.
Are we ever going to talk about those triangle things Feynman did? What was up with that? The arrows?